Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. A couple of announcements. First, as I said, the Python tutorial is already posted on the resources page on Blackboard. Please go through the tutorial very soon and go through it completely, especially the Python part. Make sure that you read the instructions that I put in the announcements, because there are parts that you might skip. But for the Python part, please do it even if you know Python already. Okay, there is an auto grading part that I want you to go through anyway. So that's one. The second one, the videos of the lectures will be available to you. Now, you know that if we record through Blackboard, it will be already automatically put on Collaborate, and I think you know how to reach it through the recordings bar on Collaborate. I will try also to put a link in the slide with the slides. As you will see now, if you go to the lectures page, you will see that there is a link to the video. I already put it. It was on WebEx, of course, so I put a link to the video. Make sure that you have access to that. If you have any problem, let me know. I'm also planning to put the videos on YouTube. So if we do that, then we don't have even to record it on Blackboard. I will record it locally on my machine and then upload it to YouTube. If you have any problem with that, okay, thank you. If you have any problem with that, please let me know. Okay. So that's it. Do you have any questions from last time? Any question? Okay, so let's start our lecture today. So last time we talked about a very indirect definition of AI through the applications, through some applications that we use in our daily life, or we see in our daily life. Today, inshallah, we'll talk more about an introduction to AI and definition of AI that is more direct than before. So we'll discuss two things: what is AI, at this time directly, and what is this course all about. So the first part, what is AI? Before we talk about what what is AI directly, let's think about AI from two sources that we also see in reality. The first source is the science fiction movies, because we all know that there is kind of at least a discussion about AI in science fiction movies. And if you think about this, you will see always, or most of the cases, AI is about robots, and robots that sometimes even come from the future to fight humans or even kill them. There's the idea of having a software that is scary and does things that we might not expect. Sometimes even in some of the movies, we see robots that are not distinguished from humans. So things like that, and this is very far from what we will discuss in this course and what actually AI is about, at least currently. So that's kind of science fiction, not reality. The other source is news, and we see also AI in news a lot. Sometimes it's talking about facts, like doing very well or beating or winning in Jeopardy, or in Go playing. Sometimes about hope of AI doing or getting more attention and making better achievements, like the talk about, or the discussion about autonomous cars, or discussion about AI in the medical domain. There is also with that some fear from what AI can do, like this saying by Elon Musk: AI is the biggest risk we face as a civilization. Also, there's a saying from Stephen Hawking, at least in the title of the news: I fear that AI may replace humans altogether. Of course, this is an exaggeration, at least for now. So, as you see, mix of facts, achievements, hopes, and fear. And again, that's not about what we will study in the course. So what we will study in the course is one of two variants. So in AI, we have two variants. The first one is called general AI. And in general AI, we are talking about machines that are conscious, that can understand its environment very well, that can act on its own, and that can do super intelligence in many tasks. So that's what we call general AI. And unfortunately, there is little progress on that and little serious research work and activity, and it's still controversial even if we will reach something like that in the near future. So again, that's not what the course will be about. Okay, so the course will not be about science fiction AI, nor news AI, nor general AI. But the course is all about what we call now AI. So in now AI, we have machines that do things in a very good way, but for specific tasks. The machines will do things that people can do now, but currently machines can't. So we develop machines to do some specific tasks. So most of the AI research is on this topic. Now, how is that different from general AI? In general AI, we're talking about super machines that can do so many things, do well in so many things. Here we're talking about building individualized machines. We have an automated system or a machine that will do well on that task, another machine that can do well on another task, and so on. Okay, so there is lots of real progress recently on that dimension. So in the now AI, we focus on developing systems for specific problems, which currently human brains can do, of course. It doesn't have to be brains, but currently humans can do. And when we talk about superhuman performance here, in that context, we mean superhuman performance in this specific task, not in everything, not in so many tasks like what we do in humans. Humans can do many things in a very good way, in correct ways, but so far we don't have this. Also, there is no or very little sense of understanding or comprehension of the task by the machines. Nevertheless, the machine, as we will see, will do very well in the specific tasks or some specific tasks. There's also, I cannot say now, no ability. That was in 2018 saying by Michael Wooldridge that there was no ability to transfer capability or generalize. There started to be to have some research on that, on how to build systems that can generalize to multiple tasks. But we are still very far from using these systems in reality. Some research started already, but we don't know if in the near future we can depend on these systems or not. They are still experimental. So that's kind of out of the scope to some extent. Maybe we will introduce something like that towards the end of the course, but most of the course, or almost all of it, will be on now AI that doesn't generalize. Okay, machines that will do specific tasks. Now, what is AI? We can define AI, as you will see, in 4 different ways that changed over time. So when we started AI, and allow me to say we as one of the AI researchers now in my field only, but of course AI started way back in the history, as we will see in this lecture. So AI is the science of making machines that think rationally. That was the first idea, okay, of having or making machines that will think rationally. What do we mean by rationally? We know, of course, what we mean by thinking, but what we mean by rationally here is to think correctly, think in an optimal way, okay? And the reason why AI started that way is that we know that there are rules of logic, or logical rules we all use in our daily lives. So if we can represent these rules in a computer and list many of them, maybe we can make machines that will really think correctly using these rules. But it turned out that that's not scalable, because we cannot list all of the possible rules that we have. It's very hard. So that led to another view of AI, which is making machines that think like people. Okay, now why we went through this approach is that we already have a very good example of intelligent system. We all have it. Every one of us has it, which is the brain, which is our brain. So if we have this example of intelligent system, why don't we mimic it? Why don't we build a system like it? We all know that there's something called reverse engineering, right? If we have a system and we don't know what is inside it, we can just try it, we can experiment with it, we can give it an input and observe the output, and then based on that, do reverse engineering, which means build a system that will do something like it. So AI researchers started to think that way. Why don't we reverse engineer the brain? But turned out that this is more about cognitive science than actually building AI. And also, it turned out that we don't really need, for building AI systems, to think like people. And I will give you an example. As we will mention in this lecture today, IBM managed to build a machine, Deep Blue, that was able to beat the world champion in chess. And it was making chess movements that humans can understand why, that can do similar things. So it was, the movements was not very strange. They were really similar to what humans actually do. But that was by no means in the same way that humans think. The machine that IBM built was completely thinking or performing in a completely different way than humans. So the point is not to mimic how humans think. Maybe we can mimic how a human act. Okay, so that was the third definition of AI. Science of making machines that act like human. So mimicking how humans behave or act. And that led to what we call Turing test. So in 1950, Alan Turing came up with this test. The test is like that. We have two rooms. Okay, one room has a machine and the other room has a human, and there's another human in between that doesn't know who is where. So he doesn't know where the machine is and where the human is, and that person in the middle has a conversation, or start to have a conversation with the two rooms, of course through maybe a keyboard or something, and screen. And the goal or the objective of the test is for the human to say which of these is the human in the middle, to say which room has the human and which room has the machine. And if the human in the middle was mistaken, that means that the machine was intelligent enough to fool the human, to act like the human. So that was the idea of acting like people, but that again didn't lead to much progress in AI, simply because we really don't we will not learn much about building machines than how humans act or behave. For example, maybe in this test I can fool the human in the middle by taking some time before I answer some specific questions, like humans. So for example, if I ask a human, what is the square root of 132? The human will take some time to answer, right? But the machine doesn't. So if I want to build a machine that acts like a human, it should slow down in providing me the answer. So this is just an example, but to give you an idea that at that stage we started to mimic humans, even if this is not, even if that doesn't mean intelligence. So the fourth approach, which we call the modern approach of AI, is not about acting like people, but acting rationally, acting in a correct way. So what we mean by acting rationally is to make what we call rational decisions. So what is rational decisions? Rational means maximally achieving predefined goals. So we said earlier that the course will be about now AI. We'll talk about specific goals or tasks. I want to build a system that will achieve that goal, but in the maximum way, in the best way. Okay, that's what we mean by rational. We don't care about how the decisions were made, but we care about what decisions are made and how good the decisions are. Okay, so that's a big difference between thinking and acting. We don't care about how the machine will think. Maybe the machine will think in a completely different way than humans think about this problem. But we care much about the outcome. We care much about the decisions, whether they are good or bad. That's what we mean by rational decisions, maximally achieving predefined goals. So the goals will be expressed in terms of what we call the utility of the outcomes, the usefulness of the outcomes, okay, the benefit from the outcomes. That's what we mean by utility. And being rational means maximizing your expected utility, maximizing your expected benefit from the decisions that you will make. And that's of course all depend on the task that you are doing. So for example, if I want to build a machine that will let's say clean the office here, a robot that will clean my office, so I might define the utility of that task is to I will give you 1 point if you clean the office, the desk, I'm sorry, if you clean the desk, another point if you clean the door, the windows, another point if you clean the tables. Okay, so if you manage to do a decision that will make all of them, so you will get the maximum utility. Of course, this is a very trivial example, but just to give you an example of what utility means here. Okay, so it's trying to characterize the outcome with respect to the task or the goal that we want to achieve. And being rational means I want to maximize this expected utility. I want to make decisions that will eventually achieve the goal in the best way possible. Of course, in the best way, we cannot define it right now because it depends a lot on the specific problem. Each problem, we will have to think about its utility and how we can maximize this utility. So the story of this course, if we want to put it in one sentence, is this one: maximize your expected utility. So we will build agents, or we will build systems, we build AI systems that will maximize its own expected utility. So all the course is about will be about defining this or exploring this statement. What do we mean by maximizing? What do we mean by utility in the context of this problem? And how can we characterize the expectation or predict the expected utility? How can we get a presentation of the utility in terms of the expectation? Okay, so I will stop here and take your questions if you have any. Any questions about what we discussed so far? Yes, Saad. Saad, pick up the mic, please. Saad, I don't hear you. Type. Any other questions? Okay, I don't hear you. Any other questions from other students? Yes, Faisal? Faisal? Okay, Faisal, go ahead, please. Okay, that's a very good question, Saad. Yes, I can hear you, and I got your question through Faisal. If that's the same question now, right? Okay. Okay, so sometimes we will not be able to get the optimal solution otherwise we would say the optimal utility. So we will just try to maximize the utility as much as we can. Okay, so in some approaches we might not find the optimal solution, and we might find the optimal solution in a very costly way. So we'll talk about these issues when we get to the approaches, but it doesn't. So the answer to your question, yes, it's not necessarily the optimal one, but the best we can do. Okay. You're welcome. Ghanem, did you have a question? Go ahead. Yes. I cannot claim that I have the full answer, but probably because it's really simple language, and there is a lot of libraries that are related to AI that were built in Python first. So that's maybe why it is widely used. But there are other languages, by the way. R also is used in AI. But Python, as you said, is the most widely one. Okay, you're welcome. Any other questions? So the ideas that we discussed are clear now so far. Okay, so let me move on and talk about the brain. Now that we said that we will not build systems that will act as humans, we don't have to act as the brains. Does that mean that the brain will be useless for us? We will not use it, or will not make use of having brains? In fact, brains are really good at making rational decisions, but not perfect. No, you know that in many cases, or in some cases, we are distracted, we get bored, we don't make good decisions. So brains, or mimicking the brains, is not the goal. And also, the brains are not modular as software, so we cannot take a part of the brain, test it, and know how it works, and put it back, and then take another part and do the same. So we cannot do reverse engineering easily with the brain, simply because we actually don't know yet how the brain works. Subhanallah. Okay, so everyone has a brain. We have millions and maybe and billions of brains over the history, but yet we were not able to know how they work, and we couldn't reverse engineer it. So there is a very famous saying, which is this one: brains are to intelligence as wings are to flight. When you see this statement, you might think that, oh, okay, I understand that because wings are important for flying, then brains are important to intelligence. Actually, the meaning is the opposite. We are saying that wings are not necessary to fly. Remember when humans started to think about building systems or building machines that fly, they think about flapping wings, right? And you know Abbas ibn Fannas. It was a big failure. And humans started to really build systems that can fly when they got rid of this idea. So flapping wings are not necessary to fly. So it doesn't mean that we have an example that we have to mimic it or to do it the same way, as long as we achieve the goal. So the goal was flying. We don't have to have wings to fly. Okay, so maybe you can think of building systems in different ways. So similarly, brains are not necessary to have intelligence. We don't have to have a brain to be intelligent. I mean, not humans, of course, but I'm talking about machines. Machines don't have to have brains, or don't have to think in a similar way to brains to be intelligent. But having said that, doesn't mean that we will not learn, or we don't learn from the brain. Actually, we learn from the brain two major lessons that we will use throughout the course. The first lesson is that the brain has memory. Okay, we all have memory, right? We remember things that happened in the past, and based on that, we make decisions in the future. So memory to AI is represented by data. So we have data. Okay, so let's make use of the data. Let's learn from the data. Okay, and the other lesson is simulation. So what do you mean by simulation here? I think all of us, in some cases, when we or before we make a decision, we think of the consequences of the decision. So let's say that the decision has two possibilities, possibility A and possibility B. So there are two possible decisions, A and B. So sometimes before we make one of them, before we say, okay, I will do A or B, we think, what if I made the A decision? What will happen based on that in the future, in reality? What will happen if I made A? Or what will happen if I made B? And based on this simulation, that didn't happen, but I'm thinking about the consequences. Based on that, I make a decision right now. So we do that all the time. We learn that from the brain, and we do it also a lot in AI. In fact, the entire first part of the course will be about that. Will be about computations that do simulation of actions and simulations of decisions. So the AI system simulate making decisions and see if this will lead me, or check if this will lead me to good utility or not, okay, to good benefit or not. Will I make benefit? Will that be useful in the future based on what will happen, based on that decision? If I were making, if I made this decision, okay. So these are two key lessons that we learned from the brain, and based on that, the course actually has two parts. Actually, you can think of these two as just one part. So the first part is intelligence from computation. As I said, the first half of the course will be about that, and the second half of the course will be divided into two subparts. Actually, this is part 2 and this is part 3. Part 2 will be about intelligence from knowledge, so representing the information that we know in what we call knowledge base, and reason on that using logical inference, okay. And the third or the second subpart of this second half of the course will be about intelligence from data, and this is, we will just touch we will have, I think, 3 or 4 weeks, like 1/4 or 1/3 of the course about that, about probabilistic reasoning in particular, and that's kind of what we call machine learning. But we will not actually get deeper into machine learning because machine learning has its own courses, of course. But we will focus more on probabilistic reasoning, inshallah, in the second part of the course. And throughout the course, of course, we will mention several AI applications. Okay. Any questions about that before we continue? Everything is clear so far? Yes, Saad. Yes. Yes. Exactly. Combinations of decisions. Okay. Do you want me to explain the course in answering this question? So the whole first part of the course will be about that. So stay tuned. Okay, there are so many approaches that we will learn about doing things that sometimes are efficient and sometimes are effective, and we will know what's the difference between efficiency and effectiveness. Okay, that's a good question. Any other questions? Raise your hand, please, Saad. Any other questions? Sorry, not raise. Turn it off. Okay, lower your hand. Other questions? Okay. So let's move on. We still have, I think, 15 minutes. That's good. Let me give you quickly a brief history of AI, just to tell you how AI evolved over time. So AI started around 1940 and 1950, the early days of AI. The first thing that was built is kind of Boolean circuit that was inspired by the brain. Okay, of course you know what Boolean circuit means. In 1950, Turing wrote a book about intelligence, and also, of course, the Turing test started to exist at that time. Then, between 1950 and 1970, there was a lot of excitement about AI and about what AI can do. So, AI systems started to be built for playing games like checkers, proving theorems, and even reason about geometry problems. In 1956, the term artificial intelligence was coined for the first time. So before that, there was nothing called artificial intelligence. But in 1956, the term appeared for the first time. Also, the first algorithm for logical reasoning was proposed in 1965. There was a lot of excitement. People thought that in very few years we will have really very good AI systems in many applications. Between 1970 and 1950, we started, or AI researchers started to think about knowledge-based approach. So why don't we put all of the information on the knowledge that we have in a specific representation and reason on that based on this knowledge to make decisions. So there was lots of work on what we call expert systems. So an example, a very famous example of expert systems is a systems that will diagnose, that will make medical diagnosis based on a knowledge base. So think of putting all of the information that doctors know about medicine, put it, instead of putting them in a book or multiple books, we put them in a computational model called knowledge base. It's like a database, but a database of knowledge, of information. If we know that, then we don't need maybe a doctor to diagnose, just ask the human some questions, or ask humans some questions about what he feels and what happened with him or her, and based on that, and based on the knowledge base that I have, I can make a diagnosis. Okay, so that was the idea. But of course, as we said earlier, that didn't scale. And actually it led to what we call AI winter. Okay, after a lot of excitement in the previous period, now we got to a lot of disappointment because that didn't scale, it didn't go in different applications, it wasn't convincing, so it was what we call AI winter. From 1990 to 2012, we started what a kind of resurgence or a revolution in AI when we started to have statistical approaches that learn from data. Okay, so we started to learn from data, and we started to model uncertainty and focus more on probabilistic learning or probabilistic inference. Again, started to have some hope, and that's why this period was called AI Spring. Okay, so we started to think about learning systems that can learn from data. From 2012 to now, we are in an excitement phase again, and this is mainly because of what we call deep learning. We have lots of data, we have powerful machines. How can we really leverage these two angles, lots of data, powerful machines, to build intelligent systems? Okay, and of course the main technology was neural networks at that stage. And we started actually to see, as we saw before and we will see right now, that AI is used in many industries and many applications. So just examples of AI again, but now under the umbrella of specific areas. So last time we mentioned individual applications. Here I want to put applications into more context of specific research area in AI, just to give you some terminology about what are the AI research areas. So in natural language processing, that's there was lots of research effort and achievements in that area recently. For example, in speech technologies, we all know or heard about Siri or maybe Alexa from Amazon doing very well automatic speech recognition and text-to-speech also, and dialogue systems. In language processing technologies, for example, question answering, you know, maybe you heard about IBM building a system called IBM Watson that was able to compete in a question answering competition with the world champion, I think around 2012 or so, and the machine won. Okay, and that was a mix of probabilistic reasoning and knowledge-based reasoning and neural networks, and so and learning from data, learning from previous experience, but it was a big success. We also use Google Translate as an example of machine translation, which is really effective. Of course, there is lots of progress in web search and in text classification, for example, spam filtering. You know, in our email boxes, sometimes we get spam. There is lots of research on how to build spam filtering systems. For example, if you are using Gmail, it does really good job in filtering out the spam emails. All of these things need really humans to look at, but now we can use our brains, of course, to reason, but now we can build systems that do well in these tasks. Computer vision, lots of progress also in computer vision, and we saw that face detection and recognition. Also in autonomous cars, when you have an image and you want to recognize the parts of in the image. For example, I want to recognize, or the machine or the car, recognize that this is the road, this is the sky, this is a tree, this is a fence, and so on. Okay, so from this image, we want to get this outcome. That's achievable, of course. Now, 3D understanding, when you have a scene, a 3D scene, again in autonomous cars, if you are in the street and you want to know how far the car in front of me is, so that's what we call 3D understanding. For each pixel in the image, I want to know how far it is from the camera. Robotics is also a very interesting field right now in AI. You know, robotics, of course, we talked about folding towels last time, playing games also, real games and autonomous cars. You know that robotics have two dimensions. There is a mechanical engineering dimension and there is AI dimension. Of course, in this course, we will focus only on the AI dimension. Game playing. We talked about chess. In 1997, there was a historical moment for AI when Deep Blue, the IBM machine, beat Garry Kasparov, the world champion at that time, in chess. And there was an open question at the time if humans can compete at all with computers after that. Of course, we didn't reach the level that we can say that خلاص, any computers can play all the games and we don't have to play any games. But there is a lot of progress there. In 2016, AlphaGo, the IBM DeepMind machine, managed to beat the world champion in Go. And Go is like it's a much harder game than chess. It's kind of the Chinese chess. It's much harder than chess. So that's why it took more time, like 19 years, from beating the world champion in chess to beat the world champion in Go. And these are just, of course, examples. And as we said last time, AI is starting to be everywhere. Now, let me go to, maybe in the last 5 or 10 minutes, we will talk more about maybe the first concrete idea in the course, which is designing rational agents. So all of the previous ones was really, previous discussion was really introduction. Now we'll talk more about the course. So the course is about designing rational agents, and what we mean by agent is that an entity that perceives and acts. Okay, an entity or an automated system or a machine or a computer that perceives, that gets an input from an environment and make actions to the environment. Okay, so let's say that I want to build a machine that will grab the apple from the tree. So it has a sensor, okay, that maybe tells it where the apple is, how far it is, and something like that. And it has an actuator that can make an action, that can actually grab the apple. Okay, of course, it needs to make a decision, rational decisions. For example, it shouldn't move to here, otherwise it will fall. So the agent has to be also rational. Okay, but before we talk about rational, let's model the agent that way. So this is the agent, this is the environment. The agent gets a perception or perceives the environment. It gets an input from the environment through the sensors and make decisions which we can represent by actions to the environment. Okay, and that's a closed loop. Make an action, perceives. Make an action, perceive. Or you can make it the other way. Perceive, make an action. Perceive, make an action. Okay, and of course, current action will depend on what we currently perceive and what the previous actions were. Okay, now the agent, as we said, has sensors and actuators. It perceives input and it produces output. This will be kind of defined for us or given to us. So we know what the task is, we know what kind of sensors the agent has, and we know what kind of actions the agent can make. So if we know all of this, what should we build in this course, or what are we building in AI? What we are building in AI is this block that takes what the agent perceives and produce what the agent should do now. Okay, so we will spend the entire course to develop and design this block. Okay, but we don't want to just design any block. We want to design a block that will give us a rational agent, an agent that will select the actions that maximize its utility. Okay, maximize the gain, maximize the benefit from the actions, trying to achieve the goal of the task. Okay, so the characteristics of the percepts and environment and the action space, all of them will guide us to think or develop or design techniques to select good decisions, to make good decisions, to make rational decisions, or make rational actions. Okay, so decisions and actions here are the same thing in this course. Okay, before we talk about this, do you have any questions? Because we will have an example now and an exercise for you to do at home. Any questions? Okay, then let me introduce this game to you. This game is called Candy Grab game. So the game is as follows. We have a pack of game pieces. You can think of them as candy. So let's say that we have a pack of candy pieces. And the game is between two players. You can also have a third one as an observer, but it's not necessary. Just two players will be enough. Now, to play the game, here are the rules of the game. We have 11 pieces on the table. Okay, so we have a table in between the two players. Each player will have his own turn. And in your turn, you will either take one or two pieces. So you have only two actions, two possible actions, either to take one piece or take two pieces. And the person that will take the last piece will win the game. Okay, so the game is very simple. We have the candies in between. Each one will have his own turn. You have to determine, of course, which one will start the game. But once we determine that, we will take turns. In my turn, in each player's turn, he or she will take one or two pieces. And the person who will take the last piece will win the game. Okay, now play that game, understand it very well, make kind of algorithm or utility or an agent, to build an agent that will make decisions. Okay, so your goal now is to build a machine that will play that game with you or with other players. So to do that, I want you to think about how you implement an agent to play this game. So I want you to build a class, use your own language. If you are not yet very familiar with Python, use Java or C++ or Python. Make it as an exercise for you to learn Python using this game. So build a class agent and implement that function. This function called getAction we'll get the state of the game. It's like perceiving what is the state of the environment now. Think about what should be the state in this game, and make an action here. Okay, so these dots, you have to implement it. You have to think what to do given any state. Okay, and first, of course, you have to need to know what should be the state of the game. And based on that, you make an action and return that action. Okay, of course, this will not be sufficient by itself. You have to maybe write a main function that will play the game. It will give turn once to the player, to the human player, and once to the computer, the machine, the agent that you will build. Okay, and let's discuss that inshallah next time, and tell me what could be the rational approach. How can you make rational decisions in this agent? We didn't study any AI method yet or approach yet. Just think clearly, think purely from your experience so far. Play the game, think of how to make rational actions and implement them. And during the course, inshallah, we will use Pac-Man game as a running example. In so many lectures you will see Pac-Man. So if you are not familiar, go through this link and you can play Pac-Man games and get familiar with it, because we will use it a lot in our course, inshallah. Okay, by that we end our lecture. Let me see if you have any questions. Mustafa. Wa alaikum assalam wa rahmatullahi wa barakatuh. No, of course, the initial state will be the start of the game. But then the state will change, of course. Yes, your function should be exactly. Your function should work with any given state. Okay, you work. And try to beat the computer if you can. Of course, try first to think how you can, if possible, to make optimal automated agents that will play this game. And if you are done with 11, make it any number. If you want to have more fun with AI. Any other questions? Muhammad. What's your last name, Muhammad? Muhammad al-Mari. أهلا بيك. Yes, start with 11. Other questions? Everything is clear? Yes, Ghanem, raise your hand please, but go ahead. Yes. Yeah, don't worry. I did it, but locally. Maybe you don't see from WebEx, but I did it locally. Any other questions? Okay, then inshallah we'll see or talk to you inshallah on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.